Welcome to the lecture series on process integration. The topic of the lecture is global and stream specific delta T minimum and its relevance. Delta T minimum is a very important factor in the design of heat exchanger networks. Delta T minimum can be accommodated in two ways. In the first way, in which it is being used in pinch analysis, is called global delta T minimum. That means, we fix up a delta T minimum which is for the whole problem and try to adhere to this delta T minimum. The other way of fixing delta T minimum can be of stream specific. That means, if the heat transfer coefficient of the stream is high, it can operate at a lower delta T minimum, and the heat transfer coefficient is less, then it can be operated at a higher delta T minimum to control the area. For example, if it is a liquid stream, that means heat transfer is taking place between two liquid streams and they have sufficiently large heat transfer coefficient, then delta T minimum or delta T for these two streams should be less. And if there are two gaseous streams, their heat transfer coefficient is less, then we have to take high value of delta T for the design, so that area is comparatively less. So, this type of thought clearly tells that the delta T minimum or the delta T between two streams should be a function of their respective heat transfer coefficient. Rather than taking a global delta T minimum, we should go for the stream specific delta T minimum. What we are going to gain if I go for a stream specific delta T minimum? The main job of pinch analysis is to distribute the driving force properly throughout the design. And this we will see in the later part of this lecture, that by taking stream specific delta T minimum, the distribution of the driving force becomes better in comparison to a case when delta T minimum is global. Let us analyze the delta T minimum. For this, we have taken a 4-stream problem, and the hot composite curve is shown by this and the cold composite curve is shown by this. We are taking vertical heat transfer, and this is a place where the hot composite curve and the closed composite curve's distance is minimum, and this minimum distance is called delta T minimum for this problem. Here we see that when you go away from the pinch, the delta T, that is driving force between the hot composite curve and the cold composite curve, increases. So, when we move in this direction away from the pinch, or we move away from the pinch in this direction, the driving force increases. This is an example where we can see if the delta T minimum is increasing, then what happens to the hot utility, cold utility and internal exchange and the total heat transacted. For this purpose, the cold composite curve can be shifted away from the hot composite curve, so that the delta T minimum increases. In this table number 2, we see that if we have taken delta T minimum as 10 degree centigrade, the hot utility requirement is 175, the cold utility requirement is 250, the internal heat exchange is 155 and the total heat exchange, which is the sum of these three, is 580 kilowatts. However, when we change delta T minimum from 10 to 20, the hot utility requirement increases from 175 to 225, cold utility requirement increases from 250 to 300 and the internal heat exchange decreases from 155 to 105 and the total heat exchange increases from 580 to 630. Similarly, when we change from 20 degree to 30 degree, the hot utility requirement rises to a value 245, the cold utility again rises to 320 units and the exchange drops down to 85 exchange and total heat exchange increases to 650. This very clearly indicates that if I increase the delta T minimum, the hot utility demand increases, the cold utility demand increases, the internal heat exchange decreases and total heat exchange increases. Now, this is a very interesting fact. Generally, it is presumed that when the driving force increases, the area requirement is less, because A is equal to Q divided by U delta T ln. So, if delta T ln is increasing, then area will decrease. However, for a heat exchanger network case, we see that if the delta T is increasing, total heat transfer also increases. That means, Q is also increasing. So, in such a case, A is equal to Q divided by U delta T ln. So, when delta T ln is increasing, then Q is also increasing. So, the reduction in the area by increasing delta T m lm is not that much, because Q is increasing, which is increasing the area of the heat exchange. So, the benefit is partial and not complete. This we have to keep in mind. So, to conclude, from the table 2, following can be concluded: the required hot and cold utility amount increases with increasing delta T minimum for a hen. The amount of internal heat exchange, that is process hot streams to process cold stream, decreases and the total heat exchange for the hen increases. This diminishes the effect of area reduction, which one can get by increasing delta T minimum of a hen. Basically, the concept that if we increase delta T minimum, then area will decrease is based on constant Q value and not for a Q which is increasing with increase in delta T minimum. Thus, a complicated interaction between delta T minimum of a hen and capital as well as operating cost takes place as given below. So, we see that the reaction between or the interaction between delta T minimum of a hen and its capital components are very critical. It cannot be explained very easily. So, let us see that what are the different interaction parameters. Now, if delta T minimum is reduced, then what happens? The amount of hot and cold utility reduces and thus its cost. So, the utility cost reduces. The second point, the amount of process to process heat exchange increases and thus the required area of heat exchangers which will be utilized for this purpose will increase and thus the fixed cost or the capital cost of the hen will increase. As overall heat exchange also decreases, it saves in terms of area and thus capital cost, because we have seen that if delta T minimum decreases, the overall heat exchange, which is has got three component, the hot utility exchange, the cold utility exchange area plus the internal heat exchange area decreases. The overall temperature driving force delta T of the hen decreases and thus the area of the heat exchangers present in hen increases and thus the fixed cost of the heat exchanger network also increases. The load of heaters and coolers decreases, because when we decrease delta T minimum, the amount of hot utility and cold utility decreases and thus the size of the heater and cooler also decreases. Thereby, its fixed cost decreases. However, the increase in the cost of heat exchangers transferring processed heat invariably outweighs the reduction of the area of heater and cooler. This we should keep in mind. Thus, the overall interaction can be judged in terms of the total annual cost. When there is a very critical or a complex interaction, then all the interactions will affect cost in different ways. Some parameters of interaction will increase cost, some parameter of interaction will decrease cost. In such a scenario, how to find out the in which way the interaction is moving? Better is that we should go for a cost computation TAC, which is affected by the interaction parameters, and then in that way we will be able to combine all the factors or effect of all the factors in the TAC, and it will convert it into a single factor and we can very easily see the effect of interaction. The most appropriate value of delta T minimum, called optimum delta T minimum, or in other words the relative position of the hot and cold composite curve, is determined by an economic trade off between the energy and capital. Once the correct economic value of delta T minimum through super targeting is known, then the energy targets in terms of hot and cold utilities are automatically fixed. If delta T minimum is fixed, then hot utility and cold utility, then heat exchange between the hot streams and cold streams all are fixed. So, finally, we get a plot like this, where when delta T minimum is increasing, capital cost is decreasing, but energy cost is increasing, and the total cost is taking a unimodal shape. Now, let us see what is delta T minimum. Further we probe into this. To show this, we have plotted 6 heat exchangers which are taking part in the heat exchanger network. For a single heat exchangers, the temperature profiles are shown by the right hand side figure, this, where temperature profiles are plotted in a T and L axis or delta H axis. We see that the cold fluid's temperature is increasing from here to here and the hot fluid's temperature is dropping down from here to here. So, we have two delta T's available at this end and this end. Say the delta T which is available at this end, we called it delta T 2 and this end is delta T 1. So, what we conclude that every heat exchangers will have two delta T values. So, if the heat exchangers are denoted as heat exchanger 1, 2, 3, 4, 5, 6 and heaters are denoted as H and coolers by C, then as per the figure 4, we will have 12 numbers of delta T's, because every heat exchanger will have two delta T's in that inlet and outlet. So, 12 heat exchangers, 6 heat exchangers will have 12 delta T values. If you presume that the heat recovery approach temperature and the exchanger minimum approach temperature are same and equal to delta T minimum, then following arguments holds good. What is that argument? Every heat exchanger will have two delta T's, like heat exchanger H x 1 has delta T 11 and delta T 12, heat exchanger 2 has delta T 21, delta T 22 like this. So, mathematically we can write the minimum of delta T 1, delta T 12, delta T 21, delta T 22, delta T 31, delta T 32, delta T 41, so on and so forth, this 12 values. Minimum this should be greater than or equal to delta T minimum. It should not be less than delta T minimum in any way. So, if this condition is satisfied, we say that delta T minimum is not violated, and if it is not satisfied, then we say that delta T minimum condition is violated in the design of the heat exchanger network. So, when we are designing for a delta T minimum, given delta T minimum, which is a global delta T minimum, we will ensure that all the delta T's of the heat exchangers should be greater or equal to this. And near the pinch, we will find that the pinch exchangers will have at least one side of delta T equal to delta T minimum. Further, it should be noted that the temperature difference between hot and cold composite curves at pinch is equal to delta T minimum. We have seen here that this difference is delta T minimum, and the delta T minimum values or the difference values are more than the delta T minimum when we go away from the pinch, and this side also when we go away from the pinch, the delta T's available in the hen are more than delta T minimum. We have seen that while designing heat exchanger network, we have to consider or we have to select a value of delta T minimum in a ad hoc fashion. Now, that ad hoc fashion delta T minimum should have some thumb rules on the basis of which we should select it. Now, this tables gives some value of delta T minimum which are collected through experience and are valid for industrial use. For oil refineries, the delta T minimum is taken generally 20 to 40 degree centigrade. Relatively low heat transfer coefficients are there in the industry, in the oil refinery, parallel composite curves in many applications, fouling of heat exchangers takes place, and that is why a 20 to 40 degree centigrade delta T minimum is enough. For petrochemicals, this delta T minimum taken is 10 to 20 degree centigrades, because reboiling and condensing duties provide better heat transfer coefficient and low fouling. We have seen that if the heat transfer coefficients are better, we can go for lower value of delta T minimum, and if they are not better or a lot of fouling is taking place, then we have to go for a higher delta T minimum. For chemical industries, it is 10 to 20 degree centigrade as for petrochemicals, and for low temperature processes this is 3 to 5 degree centigrade. Here we see a departure from the above. As refrigeration cost is very high, the delta T taken for low temperature process are less. Why? Because the power requirement for refrigeration system is very high. So, delta T minimum decreases with low refrigeration temperatures. Now, this is based on matching. Say we have steam against a process stream, then delta T minimum should be taken 10 to 20 degree centigrade. Good heat transfer coefficient for steam condensing or evaporation, and that is why it is 10 to 20 degree centigrade. Refrigeration against process stream 3 to 5 degree centigrade, because refrigeration is highly expensive. Flue gas against process streams, here we take 40 degree centigrade, because the heat transfer coefficient of flue gas is low. Flue gas against steam generation, this is 25 to 40 degree centigrade, because steam generation part will give good heat transfer coefficient, but flue gas part will give lower heat transfer coefficient. Flue gas against air, it is 50 degree centigrade, because flue gas will give you lower heat transfer coefficient and air will also give you lower heat transfer coefficient. So, delta T required is high to decrease the area. Cold water against process stream, this is 15 to 20 degree centigrade. It depends on whether or not cold water is competing against refrigerations. Summer and winter operations should be considered, because in the winter the cooling water temperature will be far less than the summer. Typical delta T values in the retrofit targeting of various refinery processes. CDU, it is 30 to 40 degree centigrade, VDU, it is 20 to 30 degree centigrade, naphtha reformer and hydro treater units 30 to 40 degree centigrades, FCC, this is 30 to 40 degree centigrade, gas oil hydro treaters and hydro treaters, it is 30 to 40 degree centigrade, residue hydro treating, this is 40 degree centigrade, and hydrogen production unit, it is 20 to 30 degree centigrades. Now, we should try to know when a low delta T minimum value can be assigned. These are the following cases where delta T minimum considered can be taken as low. A boiling or condensing steam with high heat transfer coefficient. We generally know that if the steam is boiling or condensing, its heat transfer coefficient is high. So, when we encounter high heat transfer coefficient, the delta T minimum can be less. A below ambient cryogenic stream, where economics favor maximum heat recovery to decrease expensive refrigeration cost. In such a scenario, we can take low value of delta T minimum. This I have explained earlier also, because cryogenic costs or the refrigeration cost is very high. So, we would like to recover as much energy as possible. A stream which is likely to undergo direct contact heat exchange, if direct contact heat exchange is there, so delta T minimum is almost 0. So, in that case we can take a low delta T minimum. In actual practice, following facts are taken care of while selecting delta T minimum. The shape of composite curve affects a lot the value of delta T minimum. A higher value of delta T minimum is selected if the hot and cold composite curves are almost parallel in comparison to composite curves which diverge sharply. We know that at delta T is minimum at pinch point, and if delta T is minimum, the heat exchangers which are near to the pinch point have more area, that means their size are large and also cost is large. So, if two composite curves are parallel in nature, that is hot and cold composite curves, it is appearing as if the delta T minimum is throughout the parallel position of the curve, and thus if we take delta T minimum to low, then heat exchanger area will increase drastically, and that is why if the hot and composite curves are parallel in nature, then we can choose the delta T minimum of those curves in such a way that heat transfer area decreases. This will not happen for exchangers close to pinch point, but for others also which are away from the pinch point. In system where fouling is common or heat transfer coefficients are low, higher delta T minimum values in the range of 30 to 40 degrees centigrade is taken, as it compensates the ill effect of to some extent. Now, let us see a different aspect of delta T minimum. Up till now, whatever we have learnt was a global delta T minimum. Now, we will think or we will discuss if there can be a concept of non-global minimum temperature difference and delta T minimum contribution for individual streams. Most work of Hens are based on pinch analysis. It uses a single basic parameter in the design, namely the stream independent minimum approach temperature for a heat exchanger network, which applies globally between all streams in the network. And that is why we say that pinch analysis uses global delta T minimum concept, but this concept has been challenged by many, and they have found out the drawbacks of this system. For many years this met the requirement of certain guiding values of delta T minimum have been accepted by the designer for particular industrial problems. As shown recently by Gundersen and Grossman in 1988, to insist on a single global approach temperature for all heat exchangers in the network may put the engineer in topological trap. This we will see. Further, for very different film heat transfer coefficient, it is also no longer true that strict vertical heat transfer gives the lowest area and investment cost. We have seen that if the heat transfer coefficients of the different streams in a hen differ by order of magnitude, then by considering vertical heat transfer, as in the case of bath algorithm, will not provide minimum area. Only the non-vertical heat transfer will provide minimum area in this case. Now, the concept of stream specific delta T contribution was proposed to incorporate non-vertical heat transfer for minimum area prediction. Nishimura in 1980, Ahmed et al. In 1990 proposed this. the stream specific contribution can be applied to actual temperature of the hot and cold streams to create shifted temperatures as given in equation 1 and equation 2. The equation 1 tells that T star H I, which is the shifted temperature, when we are representing the shifted temperature by putting a star or asterisk, is equal to T H I actual temperature of the stream minus delta T minimum contribution, which is specific to the ith stream or ith hot stream. Similarly, T star C j, that means shifted temperature of the cold stream j plus is equal to actual temperature of the cold stream C T C j plus delta T minimum contribution of the that cold stream j, where the T star H I and T H I are the shifted actual temperature, shifted temperature or actual temperature of the hot stream. Similarly, T star C j is the shifted temperature of the cold stream and T C j is the actual temperature of the cold stream, and delta T minimum contribution I is the delta T contribution for the hot stream and delta T minimum contribution j is the delta T minimum contribution for the cold stream. So that when ith hot stream touches the jth cold stream in a shifted composite curve, then the temperature difference delta T minimum is between these streams is delta T minimum contribution I plus delta T minimum contribution of j. That means, the temperature difference between the two streams, shifted streams, will be delta T minimum contribution of I plus delta T minimum contribution of j. Now, this shows in a figure how this shifting will take place. This is the hot stream. Now, it is vertically shifted to this stage, and this shifting is delta T minimum contribution I, and this is cold stream shifted upward by an amount delta T minimum contribution j, and this is how we compute the shifted temperatures in a case when contribution for each stream is added. Now, let us explain it with an example. Suppose if the delta T minimum contribution for liquid stream is taken to be 5 degree centigrade and that for a gas stream is taken to be 15 degree centigrade, then the liquid match would have a delta T minimum of 10 degree centigrade. Similarly, a gas match would have a delta T minimum of 30 degree centigrade and a liquid gas stream match will be delta T minimum 20 degree centigrade. The above arrangement can be included in the problem table algorithm easily. All that is required is that the appropriate delta T minimum contribution for each stream is to be allocated based on some rules, and what will be that rule we will discuss later on. So, this would give rise to different interval temperatures compared to the global minimum temperature difference. We will see that if such type of contributions are included, then how the problem differs from a case when globally delta T minimum is taken. This transformation provides a heat cascade where streams with good heat transfer coefficients can be matched with lower delta T and vice versa, and this is what we are needing, because if the stream has got a lower heat transfer coefficient, say delta T minimum or delta T taken should be higher, so that area will be less, and if the heat transfer coefficients of the streams are higher, then the lower delta T minimum or lower delta D will do the purpose. During the process, not only the interval temperatures as well as temperatures and enthalpy intervals, but also the stream subsets are changed. When we take individual contributions, then the temperature levels will change, enthalpy intervals will change, and the stream population in a enthalpy interval will also change. Moreover, a altogether new pinch, which will be called diverse pinch point, is created. The difference between the conventional pinch with global delta T minimum and the diverse pinch values are technically different. The difference in stream subset in a temperature enthalpy interval implies different pinch diagram and consequently different hens. So, we can expect that the hen which will be designed based on global temperature minimum will be different than the hen which will be designed by using the delta T minimum contribution of the different streams. Further, it is recommended that the individual film heat transfer coefficient should be taken into account at the earliest possible stage of design, when these film coefficients are order of the magnitude different than each other. That means, when order of magnitude will be high between the film heat transfer coefficients, then the contribution or individual contributions of the streams will be useful for us. In order to use stream dependent contribution to minimum approach temperatures, the streams are to be vertically shifted by a value proportional to the inverse of the individual film coefficient. This gives a rule how to find out the stream dependent contribution. Let us see in detail. The effects of this proposal should be far reaching. Not only will it make the driving force distribution smoother, but it will also provide a more realistic initial network super targeting and avoid some topological traps in the synthesis of initial heat exchangers. So, two benefits I get out of it. If I get a stream based contribution, the first is that the driving force distribution throughout the hen is smoother, and this is one of the key points of efficiency of a hen. If the distribution is not proper, then I cannot expect to get a optimum hen. The second thing is that I get a initial network which is free from topological trap. Now, let us see that what should be the rule for find out the stream contributions. Townsend in 1989, for the case of multiple hot streams matching multiple cold streams, defined stream individual delta T contributions as follow. So, delta T I into root over H I is equal to constant. He gave this rule, where delta T I is the delta T contribution for the stream I and H I is the film coefficient of the stream I. Rave and Fonio in 1991 proposed the diverse pinch concept, which uses an individual contribution delta T for each stream according to the following relationship: delta T I, that is the contribution for the ith stream, is equal to k root over h to the power minus z. Now, this relationship appears to be correct, because when H will be less, delta T I, that is the contribution of delta T minimum for ith stream will increase, and when H will be more, it will decrease. Let us take an example and see how this concept can be utilized and what is the benefit of this concept. An example was considered to show how delta T minimum contributions for individual streams can be used. For this purpose, an example of problem from Ahmad 1985 was taken up with z equal to 1 as shown below, and the value of k for equation 4 is determined by matching hot and cold utility demand as computed for delta T minimum equal to 30 degree. Now, this is a 7 stream problem which has been taken to demonstrate delta T minimum contribution as suggested by Rev and Fonio in 1991. Here we have taken delta T minimum equal to 30 degree, HU is that hot utility is 145.672 kilowatt and cold utility is 124.804 kilowatt. Now, the hot utility amount and cold utility amount is known. So, what we will do, we will find out the delta T contributions based on the equation, and for different value of k we will do it. So, when the value of k is taken 0.6, the hot utility requirement of the problem becomes 131.937 and cold utility 111.067. But when we take the k value to be 0.7099, then we see that the hot utility requirement and cold utility requirement matches. So, if I take delta T minimum contribution as per the equation shown below, that is 0.7099 into H I to the power minus 1, then I can compute the rest part of my problem. So, here the table shows the shifted temperature using delta T minimum is equal to 30 degree. Now, T S T T is being calculated and using the contribution based on the streams, the shifted T S and shifted T T is computed as shown in these two columns. The shifted temperatures using delta T minimum contribution for individual streams. This is the shifted temperatures, these are the actual temperatures, and this is the delta T minimum contribution for different streams. For H 1 this is 7.099, for H 2 it is 17.748 and so on so forth. And you will see here if the heat transfer coefficient of the stream is less, the contribution is more, and if the heat transfer coefficient is more, the contribution is less. And these are the Cp values, and this is the H value. You see here the H is 0.1, the contribution is 7.099. When H decreases 10 times, about 0.04, the contribution increases. Now, if we see at the different temperatures, the temperature intervals, we find the temperature intervals shown here and the temperature intervals shown here are different. This part is a global delta Tm 30 degree taken, and here for this part delta T minimum contribution for individual streams are taken. Then also we see that the streams start from different temperature level to different temperature level. If you see here, H 3 starts from 328 degree centigrade to 75 degree centigrade, here H 3 starts from 266.4 degree centigrade to 97 degree centigrade. Further, we see that if you see the third interval or fourth interval or fifth interval, the number of streams are different. So, here we find that as here you see the the C1 starts from here to here, but however the C1 starts from here to here. So, here we have 3 streams, and if we consider here we have 2 streams, here we have 1 stream, here we have 2 streams. So, the stream contribution in a particular temperature interval also changes. So, please observe the difference in stream subsets in a temperature enthalpy interval, which implies different pinch designs and consequently different hens. So, if I design a hen based on this, it will be different. If I design a hen based on this, it will be different. Now, if I plot the hot and cold composite curve from my global delta T minimum, which is 30 degree, this looks like this. And if for the delta T minimum contribution of individual streams, this looks like this. So, there is a lot of difference between these 2 plots. Now, this shows minimum heat flow at interval temperatures for delta T minimum. When global delta T minimum is taken, you find that minimum heat flow also changes in comparison to this. Though minimum hot utility requirement and minimum cold utility requirements are the same for both problems, but internal heat flow changes. The pinch point is here is 144, the pinch point here is 151.90. So, pinch point also changes for both the problems. Now, my GCC for global delta T minimum equal to 30 degree looks like this, and the second pass shows for delta T minimum contribution for individual. These 2 also changes a lot. This is the driving force plot for global delta T minimum equal to 30 degree centigrade, and where the delta T minimum contribution for individual streams are taken up. What is the conclusion? The conclusion is that from figure 6 and 9 and table 8 and 10, it is clear that when delta T minimum contribution for individual streams are applied, not only the interval temperatures as well as the temperatures and enthalpy intervals, but also the stream subsets are changed, that we have seen. Moreover, altogether a new pinch called diverse pinch point is created. The difference between the conventional pinch with global delta T minimum and the diverse pinch values are technically different. This we have also observed. The difference in stream subsets in a temperature or enthalpy interval implies different pinch design and consequently different hens. So, it proves that in both the methods different hens will be created and they will not be alike. The effect of using individual delta T contributions for individual streams, the distribution of the heat transfer driving force is smoother. When we take delta T minimum contribution, my distribution of driving force is better than the earlier one when global delta T minimum is considered. The same effect can be seen from the lower smoother plot in figure 9. This shows that it is smoother, delta the driving force is smoother. The last point, which is very important, area computed using diverse pinch are close to that computed using linear programming and are less than that obtained using the bath estimation, especially for moderate and high duties of N. This shows that if we are going for delta T minimum contribution for each individual streams, then the area computed will be less than if it is computed using bath algorithm, which uses vertical heat transfer and global delta T minimum. And it is almost equal to the linear programming results, which does not consider vertical heat transfer. So, if the heat transfer coefficients are differing, then it is better to use delta T minimum contribution for individual streams, because we will get less area of the hen if we design it using this condition. Thank you.